Okay, so we left off last time finishing up a discussion of unsupervised learning. So far we've been talking about neural networks and different ways you train neural networks using sort of supervision. And so the idea behind supervision was this: I give you a data set where I've got input data and desired output data, and the training task is to have the neural network best approximate a function that for those input data will give me the same output data and hopefully generalize. So if I give you input data that is similar to the input data that I trained on, but not quite exactly the input data, I still get an output that would make sense, that would be consistent with that data set. And we talked about this can be viewed in terms of a linear regression or a nonlinear regression, or you can then add thresholding type constructs or different activation functions and different transformations basically of an output space. And then that turns it into like a classification problem. And so, oh yeah, the virtual background behind me is another shot of the Weaver ants from here at ASU. So I think they're just doing a different structure than the one that was drawn before. So then we transitioned to Q learning, and so how Q learning, which comes from supervised learning or from reinforcement learning, can make use of these approximations inside it. And so deep Q learning is this idea that I can take a deep neural network to learn a mapping from action state space into quality space. And so we talked about deep neural networks as one way to do that. The older school way of doing it is to actually build functions that have parameters that are shaped in a kind of gradient descent or even back propagation-y type way. And so when deep neural networks became more plausible for these reinforcement learning applications, then people realized, well, it's rather than having this function kind of change itself, why don't I just have a neural network approximate this function and just use the neural network as my surrogate for that? And then we transitioned to unsupervised learning. And so this is the idea that there is no reward. I just give the neural network data and it has to figure out interesting ways in which to sort of reshape this data and going from input to output. And so we gave these clustering examples where if you've got some feature of the data here and some other feature of the data here, and you end up plotting all of your data that you give to the neural network, then maybe the neural network starts noticing that there are clusters that form. And so hopefully the neural network comes out and it labels all of these with a particular number, let's say 1, all of these with a particular number, let's say 2, maybe then it labels these things as 3 and 4. And so you could imagine then, clustering and anomaly detection as two very related applications. Or you could imagine there are other ways that you could maybe link neural networks together so that they become you can even take supervised learning approaches, and the data sets that are generated that are put into the supervised learners are actually generated by other neural networks. And so you have a neural network that's trying to best approximate a function, and then another neural network that's trying to best approximate data that would be used to train that function. And these two things can go back and forth. And so when you can remove supervision by kind of closing the loop around two neural networks so that they end up becoming their own mutual challenges, then these are these so-called generative adversarial networks, or GANs, which are very popular right now. And so you could view all of this as a kind of computational creativity. When you are trying to use computers to find patterns that you yourself may not have been able to find. So before, you defined the outputs you wanted. Here, you don't quite know what outputs you want. And so these are ways in which you can get a computer to generate outputs that hopefully afterwards, if you look back on, end up being useful and interesting outputs. And so that's kind of the broad realm of this unsupervised learning. And so I wanted to give one more application of that today and a more concrete example of one way that you could do that, and that's multidimensional scaling. Now, before I get into that, I just wanted to see, are there any questions or comments from that previous discussion as we transitioned from supervised learning to reinforcement learning to unsupervised learning and clustering? Okay. All right. So let's think about this, this problem, which is common in data science, of multidimensional scaling. Or MDS. And so multidimensional scaling is the idea that you've got a data set that, let's say, it has a wide range of, has many dimensions. And so I might have data that I can express in at least 3 dimensions. So I've got my x1, my x2, my x3, and I've got data points. So each piece of data can be measured in these 3 different ways. And so I've got height, length, velocity, maybe I've got, birth date. I mean, you can come up with all sorts of different components of data that could go into a high dimensional view of these things. And you've got a lot of these things. So maybe you've got, it's a big data application and there's a bunch of these things all over. And it becomes difficult to visualize. So even before asking, are there clusters or anything like that, just as a human, it's difficult to look at these 3 or more dimensions and be able to make sense of if there's any structure there. So rather than just going and asking the computer, give me clusters, in order for me to build confidence in the solutions or to better understand the solutions that the computer has, then another question could be is, well, I would have an easier time understanding these data if I could somehow create an approximation of them that are in a different number of dimensions. And pardon me 1 second, I've got a barking dog that I have to, I think, move or open a door for. So just a second. Thanks. Oh. Yeah, that's not the first time that's happened. In fact, if anyone is interested, I think I've got that's Fritz right there, or I could say that's a picture of him right there. Yeah, he's cute. A little black and white. I'll leave that one up maybe. All right, so so the idea would be that I have this complex space, but I know that it's going to be easier for me, or maybe it'll be easier for some downstream processing if I had a way to somehow get rid of all of these 10 dimensions and just come up with a transformation which turn these into, say, 2 or 3 dimensions that somehow doesn't upset the relationships between the data points, even though the dimensions I create might be difficult to interpret and what they mean. And so, so I have this like 3-dimensional example over here, and let's say I'd like to then turn it in to a 2-dimensional example, where maybe I'll make this y1 and y2, where in my 2-dimensional example, these points show up on a plane, and I could label, so this point here might go down to this point down here, this point might map to this point, maybe this point over here maps to this point, and so on. But I've managed to flatten these things onto a 2-dimensional plane, and then hopefully when I say certain relationships are still invariant through this transformation or approximately invariant. So as an example, it might be that the distance between these 2 points, I could measure it in 10-dimensional space. I could use a Euclidean distance, and I could measure, just to make it clear, I can measure maybe this distance here. And I might want to make sure that in this new 2-dimensional space, that the distance is approximately the same. So is there a way for, if you imagine a bunch of springs that are kind of tied to each of these points in multidimensional space, is there a way that I can smash all these things together so that I know it's going to deform themselves, but maybe the relative spring tensions will roughly be the same, so that although they're now expressed on a lower dimensional space, they have their relative relationship to each other is maintained. And so that's the multi-dimensional scaling. And we can see that of course this is a doctored example that I just drew these dots randomly, but this is the type of thing that often happens, is that if once you take things from the high dimensional space, you might not be able to see things like clusters in this space, but when you go over to this other space, this 2-dimensional space, then you start seeing that actually now it's pretty clear that there are clusters in these groups, and even maybe there's some sort of obvious linear structure or simplex or something like that that separates these things up. So in this new space, I can visualize the separation among these a lot easier. And there are a bunch of different ways to do multidimensional scaling. So those of you who've taken a statistics course might be familiar with, for example, principal component analysis, or PCA. And the idea behind PCA is this is basically a linear algebra problem. So the thought is if I have my data set, and let's say I'm going to use X and Y here, but I don't mean Y in terms of the transform coordinates. I'm going to have 2 data points, X and Y are my 2 data points. And so if I've got these 2 data points, X and Y, then you can represent the kind of this inner product you can view as the angle between. You could view this as X as a vector and Y as a vector. And if I could come up with a transformation, it's a question here come through the chat. The identification of clusters upon dimensionality reduction is obvious only upon visualization, or do we hope it will form good clusters upon reduction? The reason that you have for dimensionality reduction purely could be just for visualization. Or you might, there's a bunch of different reasons why you might have a very complicated representation and you would like to extract, like maybe you just think, maybe your hypothesis is that although there are 10 dimensions of data here, those dimensions are related to each other, or there's a phenomenon here which really only has 2 degrees of freedom. So if your insight is that there's only 2 degrees of freedom here, then that suggests that I should be able to find a transformation to 2-dimensional space where hopefully one dimension represents 1 degree of freedom, the other dimension, the other degree of freedom. So, as an example, it might be that there's a fixed amount of energy in a system. And so the energy constraint of a system, greatly constrains the motion of the particles, for example. And there might also be a constraint that there's a spatial constraint. So I know that the particles have to be within a box, or maybe they have to be, they exist along a line. So maybe I put marbles in a tube, and those marbles are rolling along inside that tube. And I fix the amount of energy available to those marbles, and I fix that they have to roll along this tube. Now, if I just gather coordinates of those marbles that are rolling inside this tube in space, so if I were to draw that tube, so here's my kind of example here, there's a tube in space, and I've got marbles that are rolling inside this tube in space. And so here they're constrained in space, and then they're also maybe constrained in energy. Now, it's possible that in my data set, I can't see the tube. All I can see is the marbles. And so I see these marbles moving around. And if I just look at all of the different data I collect on them, their position, their velocity, all of these different things, it looks like they could be moving in 3 space in an unconstrained way. But if I think that, I'm not quite sure, but it kind of looks like they're moving along a line there, and it kind of looks like they're not moving at every speed, that they're kind of like, there's sort of a consistency in their speeds, I might say, is there a lower dimensional representation of this that reveals to me that there's actually reduced degrees of freedom in their motion? Even though I could take data in 10 dimensions, they only can move in 2 dimensions. So then if I can find a way to reduce this down to 2 dimensions, then I might find that actually all these data are in whatever these 2 dimensions are. So I'll call this D1 and D2, that all these data are, maybe they actually fit, they all cluster around a particular point in this D1, D2 space, which shows that they are constrained in their energy and constrained in their spatial orientation. And so this clustering gives me more scientific insight into what I can then ask, well, then what the heck is this dimension? Well, if I then figure out the transformation from 10-dimensional space to this dimension, then maybe that shows me the formula for this line, for this tube. And so figuring out that formula actually tells me something about the shape of the admissible paths, and maybe figuring out the formula translating 10-dimensional space into this dimension, D2, maybe that translation, or that, I don't want to say translation, maybe that transformation actually gives me a formula for the energy in the system. And so now these formulas end up forming theories that I can use to make new predictions about how the system might operate in the future. So sometimes dimensionality reduction just allows us to go from an unconstrained perspective of a system to a theoretically constrained perspective of a system. So if we observe that things are efficiently reduced in their representation, then that gives us an insight that there is theories that we can build to explain that constraints. If we find that the best we can do is 10 dimensions, then that means that maybe there is no hidden information there. So I hope that kind of helps. Clustering is one example, but there's a bunch of different reasons why you might want to reduce the dimensionality. Okay, so in PCA, the idea would be if I got my data points, X and Y, and I want to create a transformation, I'll call T, that that transforms X and Y. So it may rotate them, it may move them around a little bit, but my goal in PCA is to make sure that the transformation of X and Y maintains the angle between them. And so the idea here is, it turns out that or I guess not only angle, but angle and length. So it maintains angle and maintains length. X, Y, Z, whoever I'm going through this transformation. So I would like a transformation that doesn't shrink or stretch out vectors, but effectively rotates them, and does it in such a way that in PCA's sense, the dimensions are then going to be ordered in terms of how much variance that they explain. So PCA by itself does not do dimensionality reduction. It just reorders my dimensions so that they're ranked by variance. So then the goal, and then I'll get to the multidimensional scaling here in a second, reorder, or not necessarily reorder dimensions, but I'll say recreate dimensions ordered by variance they explain. I'll say maybe amount of variance they explain. So what I mean by that is Could you please, I'm reading a question in the chat. Could you please repeat what you meant by, if the dimension is not reducible, then it does not have any hidden parameters? Or I didn't mean hidden parameters, but hidden structure. So the thought is that if you have a data set represented in 10 dimensions, and if you find that you can efficiently capture all of the, let's say, movement, if let's say this data set is time slices, and if you can efficiently compress your 10-dimensional data into a 2-dimensional representation, so that you can effectively predict everything that's going to happen in the 10-dimensional set using the 2-dimensional set, then that implies that there is a hidden structure inside your data set, that the data doesn't necessarily, that the how you took the data doesn't capture that structure. But when you look at all of the data, it doesn't kind of move around in full 10-dimensional space. So it's almost like I could measure the volume of a cup, but I could also measure the size of a cup. And I could also measure the surface area of a cup. And these are different numbers, but if we took a bunch of different cups, we would find that volume, I don't know, height and surface area are all related to each other very strongly. So even though I've taken a lot of information, I've recorded a lot of information about a cup, it turns out that there's a degeneracy in that the shape of a cup is such that once I know the height of a cup, I can predict a lot about the volume of a cup just by knowing the height of a cup. And so I can probably get rid of 2 of my dimensions and just reduce it to a 1-dimensional representation of a cup. And I might lose a little bit of info, but just knowing the height of this coffee cup allows me to predict all of the other things around it. So I can reduce the dimensionality. Now, if it is the case that I have something else that is less regular, like some arbitrary headphone case or something like that, simply knowing the height of a headphone case doesn't necessarily tell me anything else about the headphone case. And so maybe with the headphone case, I need to know the height, the width, the volume. I need all of those parameters. And if I throw away one of them, I lose the essence of the headphone case. And so in that case, there's no hidden structure. There's no hidden correlation between the variables. And that's what the multidimensional scaling is so good at, is when there is hidden structure, throwing away all the degeneracy so you're only left with the salient features. Does that help? Great. All right, so the amount of variance is what we explained. So in PCA, I have a cloud of data, so in multi-dimensions. And so it's some cloud that's extending out. So you can imagine this is some type of rugby ball, or so I'll just draw kind of something around this way and then kind of implying that it has depth to it. So imagine this is like a football or rugby ball or melon, whatever 3-dimensional ovoid shape that you'd like, egg, trying to reduce the cultural bias in the lecture. So whatever you can imagine, some oval sort of shape. And, but that oval shape is kind of oriented obliquely to these 3 dimensions. And so the idea here in PCA is that, can I find a way to kind of rotate the rugby ball so that I still might have 3 dimensions, but the first dimension, so I'll call this D1, is going to be kind of like the long axis of the melon, or the long axis of the egg. And so this is the second dimension is going to be like the next most prominent dimension. And then the third dimension will be the next most prominent dimension. So the idea here is that information about D1 explains there's sort of the most variance in this cloud. It comes along the D1 axis. And so if I were to measure how variable these points are, most of the variation comes along the longitudinal axis of this melon. And then the rest of the variance comes on the kind of tangential axis, and then anything left over is the kind of the other sort of tangential axis that is maybe a little flatter, if this is more of a pancake type shaped melon. And so by reorienting it this way, it provides me useful dimensions. So if I just take an egg, an arbitrary x, y, so I guess right-hand rule, maybe x, y, z dimensions, in this space, x, y, and z, x, y, and z aren't really useful in terms of the melon. So what is the x dimension? Well, the x dimension is just some coordinate in space, and the way my melon is oriented kind of affects whatever the heck x means. And so what PCA does is it takes the melon and it lays it down so that we can all agree that our first dimension is the long axis of the melon. Our second dimension is the fatter, the next fattest axis, and so on and so forth. So, so you can think of PCA as a rotation, and I guess in translation of data. And I say, I just showed rotation here, but in reality, you would imagine the origin being in the middle of the melon. And so PCA is great because how does PCA judge the variance along a dimension is the question here. So this transformation, T here, is specially constructed so that the dimensions are chosen to maximize the variance along the first dimension. And then so I'm not going into all of the details on how you build the PCA transformation, but if you did pick up a good book on stochastic processes, or even just a nice graduate level book on linear algebra or something like that, they'd probably have PCA in there as an example where you can create this linear transformation that, just like you can create linear transformations that capture least squares. So, like least squares is, you want to minimize the distance between things, and you can kind of think of that as a projection operator in this kind of linear space. And so what we're creating is another one of these operators that projects from the XY space to the D1, D2 space. And you can design that projection so that it maximizes variance along 1, 2, and 3 dimensions. And it's kind of outside of the scope of things that I want to talk about here to say how you do that. But there is a very mechanistic way to build that transformation, to sort of decompose the data along these dimensions. And this is not that different. This is related to eigenvalue decomposition. And so again, if you remember from linear algebra, there are ways to take a matrix and then break that matrix up into these eigenspaces or eigenvectors, and then you can represent that matrices effect on vectors in this new space where you can order the eigenvectors by their kind of maximal effect on a vector that you're multiplying by that matrix. And you're actually doing something nearly identical here, where you view the data set as taking a kind of input variance in and then spreading it out over the variance in the data. And once you have this kind of matrix representation of your data set, then you're able to decompose that matrix into these eigenvectors, where each eigenvector or eigenspace represents the dimensions along which you have this maximal variance decomposition. So yeah, it's again, I don't want to go into the details here, but if you kind of try to think it through here and you look up a good reference on PCA, then I think you'll see that PCA is a fairly straightforward application of eigenvalue decomposition or spectral decomposition along a sort of variance space. Great. Okay, so that's a useful way to rotate our data. Now, if your data happen to be such that most of your variants are explained by the first dimension and the second dimension, so we can associate a number with this. So we can say that there's a certain amount of variance. We'll just come up with a scalar value for variance. There's a certain amount of noise in this cloud. And we can say that 40% of that noise, or let's say we'll say 70% of that noise is explained by D1. And then we can say that 25% is explained by D2. And the third dimension in this new representation is only 5%. So all three dimensions are useful, but once you know dimensions 1 and 2, there's not a whole lot left over for that third dimension. And so it may be that you can just get rid of this dimension over here, this third dimension, and just represent things in terms of these first two dimensions. And that's very often what people do. They say, we took a PCA of our data, and we could explain 85% of the variance with principal components 1 and 2. And so here is a representation of our data set only showing you principal components 1 and 2. It just throws out the rest of the dimensions. And then that becomes a multidimensional scaling. That is one way to do it. Now, I mentioned that PCAs are so there are any questions about that? So I'm now going to use neural networks to generalize this to kind of a more nonlinear way to do exactly that, reducing the dimensions and throwing out data. So are there any questions about this idea of PCA? Is this the same as feature selection? And so there's a question about feature selection in the question there. And there are a number of methods for feature selection that are effectively doing this type of thing, sure. And so you can say, I have found, I took 100 different, I measured 100 different things. I have no idea which one of these things is useful. Usually in feature selection, you also throw in some sort of response variable, and you're asking which one of these features is sort of, can I come up with a reduced set of features that will be most explanatory when dealing with this output variable? And so feature selection is also, and then once you have that subset of features, then there's something called model selection, which will then say, of all of the models that use this subset of features, which model, which relationship of these things is a best best captures the relationship between these features and that output variable. And they are all certainly related to these. There are back of the envelope ways of using PCAs to do feature selection, but most feature selection algorithms usually have their own je ne sais quoi about them, where they're a little bit more than just like a PCA. So lasso is sort of I'll just mention it as a side for feature selection is, lasso is a very common, or those of you that are into graph networks now, Glasso is the kind of graph version of lasso. So these are all very important for feature, or very useful for feature selection. And I will say that your insight, your intuition that there is relationships here is good, but I don't want to say outright that this is feature selection. I'd say this is just strongly related to feature selection. And then I see a question here. I talked about maintaining angles in reduced dimensional space. I talk of PCAs. Anything that is constant when we perform PCAs, but by constant, I mean that if you maintain all of the dimensions, so you don't throw out any of the higher order components, then the points, the length of all of the points in PCA space and the angles between them will be maintained, because it is this property up here is a PCA property. So this is something that will be maintained. So that's the benefit of PCAs is this. But once you use PCAs for dimensionality reduction, that goes out the window, because if this dimension explains a lot of your variance and you throw that out, we have no guarantees that the remaining dimensions will still maintain those distances and those angles. But as long as the remaining variance to be explored or explained by the dimensions you throw out are not that high, then this approach of throwing out all but the first 2 or 3 principal components is not a terrible one. All right, so any other questions about this PCA? Okay. All right, so how do we use, I brought PCAs up to sort of say, to bring up the problem of, um, can we use unsupervised learning to build, I'll say, PCA-like dimensionality reduction in other words, I see, what is the T on the oval? Sorry about that. The T on the oval. So I don't know if you're referring to the over here on the left or over here on the right. Oh, transformation, this T here. And so at least you're referring to this T, that T is just a transformation, it's just a linear transformation. This is just a mark. I didn't mean for that to look like a letter, if that's what you're referring to. And so I guess I could write underneath here that if you start with X, Y, and Z coordinates on this side, then on this side you have T, X, Y, and Z coordinates, and that gives you your D1, D2, and D3 coordinates. Okay. All right. Great. All right, I'm going to flip. And so the structure that some of you might already be familiar with this. So just to kind of see if anybody's so does anyone already does anyone anticipate, those of you who've already used neural networks to do similar things, is anyone out there that's anticipating the neural network structure I'm about to introduce here? Great, I see a couple of them. Autoencoders are coming up. And so this, and just sort of, this is the autoencoder is meant to be a nonlinear PCA. In fact, I think if you use linear activation functions in an autoencoder, it actually reduces to a PCA, and with throwing out dimensions here. And so the idea, this kind of ingenious idea behind the autoencoder is that you have an input set of data, and I bring that in, and I've got, you know, this is just a multi-layer. You can think of this as a multi-layer perceptron, and I've got these different layers, and so I've got my input data coming in as X, and then I create a layer similar to kind of convolutional neural networks that's coarser than this input layer. So it's, you know, smaller than this input layer. And so it then has less representational space as the layer that the input is connected to. And then I have a really tiny layer that I might connect to inside that. And this layer inside here sets up these kind of latent variables that are meant to be a reduced dimensional representation of my data. And so then the question is, how the heck do I train my neural network to know what are the right way to set up these synaptic weights so that I effectively extract this information? And the way you do that is by building a decoder that looks just like your encoder, but then compare what it decodes to your inputs, and then keep adjusting the weights until the thing you decoded looks like the thing you encoded. And so, in other words, and I'm going to draw this in a second, but if I have my coffee cup, I would like to represent my coffee cup as just a height, but then that requires me building a decoder that, given a height, will then reproduce a coffee cup. In that decoder, I'm going to compare the coffee cup that it builds to the coffee cup that I inputted. And if the dimensions of the, height or whatever I want my z dimensions to be, that I don't know ahead of time, if I've ended up capturing all of those, then the decoder that produces my approximation of the cup will look just like the cup that came in. So the idea is I'm going to then create another couple of layers here. So that will mirror the layers on the input side. And I'll call this output layer X prime. And this you can view as an output, but I want the output to look like the input. And so the real output is actually the latent variables in Z. So I will say that ultimately, Z has reduced dimension representation of input. So this is like my D1 and D2. But to get there, then I am going to compare this. I am basically going to create a loss function which connects the X prime and X together. So you can think of a loss function based on minimizing the difference X minus X prime, and I'm just taking the norm here. And so this turns this into a supervised learning task. But the beauty of it is that the desired output is the input. And so we still group this under sort of an unsupervised learning, and that the system is coming up with this reduced dimension here by itself, and I'm only providing it an input. But by providing it an input, my input is the desired output. So it effectively closes the loop from output to input. And so for every input, I see what the output is, calculate a loss, use backpropagation, for example, and from backpropagation, I can train this neural network, and I do that over and over again. And eventually, once I start producing outputs which look like the inputs, then I can forget about the real output because I don't actually care about that. And instead, what I export to the user is actually the latent variable Z. So Z becomes the new output. And so the X prime, that decoder, was only there for the training step. And what I actually need for execution is just this reduced dimension down here. And it's possible to show that if you've got linear activation functions in this whole process here, then solving this problem with, say, a least squares loss function is equivalent to doing a PCA and throwing out a bunch of dimensions. And so this really is a nonlinear PCA, or a generalization of PCAs. And we still would view it because, I'll say, because input is desired output, this is still unsupervised, at least from my perspective. So this is a tool of getting a creative representation out of the middle of a neural network that you may not have anticipated. Absolutely, autoencoders have applications in computer vision. So I have as one example, I have a student in my lab who looks at a lot of video data of ants. And of ants behaving and moving around. And so each ant has its own peculiarities if you look at a particular video, but there sort of is a salient features of an ant. And so he will sometimes use autoencoders to take ant video in, and he'll look at generated video that comes out of the autoencoder. So this is, you know, so this is it. Well, I won't get into too many details, but generated video that comes out, and then this ends up producing a reduced order image, whatever an image would, a reduced set of features that really characterize what is an ant. And what's amazing about this is then if you then, he can then use a decoder to then show me the image that pops out of the decoder. And it is kind of a cartoon-like ant. And so you have, coming into it, you have this like nice looking picture of an ant that, you know, has, you know, its antennae are in different, you know, positions, and it's got these 6 legs and whatever, but there's slight variations from ant to ant to ant. It goes through this whole process, and then the thing that comes out on the output ends up being kind of a cartoon ant that's in the same orientation as the input ant, but maybe it loses some of its variation. Like maybe its 2 antennae are now you know, straight out. They don't kind of have the little bit of bends anymore. So but that's good, because it sort of tells us like, this is the prototype of an ant. We don't need to pay attention to where the antennae are, because really what characterizes an ant is the fact that it has antennae, and it has 6 legs, and it has these 2 body segments. So absolutely, you see autoencoders showing up in computer vision. There's a bunch of different cases, and primarily they come up because downstream logic that you want to implement, you often want to look at a reduced set of features and a reduced representation in order to make it more computationally tractable. And you can also view this as a filter, filtering out noise. So you don't want to overfit on noise from your input data. And so this sieve ends up kind of pushing your data through the sieve, and the stuff that comes out the holes are the kind of important features of your data, and the stuff that gets stuck in the upper part of the sieve is the noise that you can then discard, and that's effectively what's happening here. So any other questions about this idea of the autoencoder? The auto being that it's a self-encoder. So it comes up with an encoding, and then it decodes that to evaluate how good that encoding is, compares the decoded version to the desired input, and then uses that comparison to guide whether it needs to modify its encoding. So I guess I could put that under autoencoder. You could view this as self-encoder. Okay. And so this is a way to use neural networks to do dimensionality reduction. And so that was meant to be kind of my last example of unsupervised learning, before we now can move into thinking about how to do this training on the fly with Hebbian learning. So far we've been talking about these cases where I train, and then I deploy. And so how do I kind of think about building neural networks that learn at kind of life history scales? So before we get there, I just want to make sure, is this clear, this idea of this nonlinear PCA, dimensionality reduction, autoencoders? And autoencoders have been around for a long time. You can view the encoder side as a noise. So there's a question in the chat. So the decoder side is a noise remover. I would call, just to be clear, I would call this is the encoder. This over here is the decoder. And I would view the encoder as the thing that is removing the noise. And so you could view this as removing noise. And by noise, I mean features that are not important, features that are just background data, that they aren't important to the task of matching generic input to generic output. So this I would view as a hopefully clean representation And then we then look at the representation coming out of it over here. So that's where we evaluate on the output side. Okay, cool. All right. So those are, again, a bunch of different ways we take neural networks, give them a bunch of data, and then see what they come up with with these data. Now, they're ideally, if we really want neural networks to behave like living systems, then we want those neural networks to have some plasticity over their experience. So I'm gonna, if I've not used this term a lot before, and I should, introduce this term plasticity. So, from mechanics, we've got elastic regions and plastic regions. And so a material is elastic if you push on it and it pops back and doesn't look like anything happened afterwards. And then a plastic region is something that you push on it and it stays deformed. So in learning is a representation, or is related like a dough. Like, yeah, if you push on dough, then it stays deformed. That's sort of in the plastic region. And so in neural networks, their experiences with the world may push on them to change how they work, and then they may stay changed. So that allows your robot to learn things over time, as opposed to just learning them at the factory and then get deployed. And so, so this is more broadly fits under associative learning from the kind of psychological literature. And we are going to then focus here on a particular mechanism of associative learning called Hebbian learning, named after somebody named Hebb. So Donald Hebb, but and the quote that you often see associated with this, although this did not come from Hebb himself, was neurons wire together if they fire together, which sometimes is simplified to something that is somehow pithier, although similar number of words, like those that fire together wire together. It's another way you could say this, but I think the original quote was neurons wire together if they fire together. More clear to be a wire. So the idea here is if we imagine a neuron. So this is my neuron, my cell body. It's got this axon, and so stuff's going on with this axon. There's another neuron nearby, and so there's our other neuron, and there are there are opportunities here for a synapse between A and B. And so the question is, how does nature, or how does biology, adjust the weights of these synapses? And so the idea behind Hebbian learning is that if you look at the temporal pattern of the firing of two neurons, and you use that temporal patterning to determine whether you should increase the synaptic connection between them or decrease the synaptic connection. And so the idea here is, like, if A fires very close to when B fires, but slightly before B, the connection, you can think of this as a weight, maybe you can view this as the weight from A felt by B, between A and B is increased. So if A fires and then B just happens to fire, B may not actually be influenced by A that much, but it happens to have one of these synaptic gaps between them. So it has the opportunity to be influenced by A. And so then the question is, will B become more sensitive to A? Well, if it so happens that B fired just after A fired, so it can detect that A is still in this region where it's firing, and then B fires, then B will then become more sensitive to A. So in the future, then when A fires, then A will become more of a trigger for B, so the B can fire even more closely to A. But then likewise, you can actually have negative interactions. And so if the opposite thing happens, so that these two neurons don't fire in that order. So you might get a firing of B, but not of A, or the firing of B happens well before A. Then you can actually, if there was a connection between A and B, then that connection can be reduced. So, so I could say maybe and vice versa. If connection exists between A and B fires before or without A, connection will weaken. And so you can imagine that as the neural networks are moving, then this is reinforcing and inhibiting these weights so that they become more or less efficient at these at this operation over time. And so, and I'll show you in a second how this is very useful for pattern learning, but I do want to introduce this term, STDP, which is spike timing dependent plasticity. There's that term, plasticity, again. And so this STDP is a generalization of Hebbian learning. And so this basically is the same idea I was just saying, of a spike is on an input is before but close to an output, the input weight will increase. If it's after, the input weight will decrease, which is just what I've been saying down here. So this here is just STDP, which in spiking neural networks, which we'll introduce by the end of this lecture or the beginning of next time, this is the primary mechanism that spiking neural networks have been using in order to reinforce these connections. And so they're mimicking this STDP, spike timing dependent plasticity. So you could imagine for non-spiking neural networks that you could come up with weight update rules that run in parallel with your neural network that kind of look like gradient descent type algorithms. So they've got a kind of learning rate. And so I can write like one of those, I might do it on the next page here. So I could say, you know, for example, implementation for a conventional artificial neural network. And this is of spike timing dependent plasticity or Hebbian learning. I guess it's not, I'm going to emphasize the Hebbian learning part because there's no spiking in the conventional neural networks. And so I'm going to maybe highlight this Hebbian learning is really what I'm talking about here. Is that you could come up with a weight update rule So let's say I've got a neuron I, I've got a neuron J, I've got a weight Wij, which represents I's influence on J's firing. And so, maybe I then write, so you could imagine the value at neuron I is Xi, the value at neuron J is Xj. You can think of that like post-activation function. And so it's a weight update rule. So we can say that the weight of Ij at the next time period is equal to the previous weight at this time period, plus, and I'll just say some eta xi k, xj k, where this here is like a learning rate. And again, this is the output of I and J activation functions. And so you can imagine that this update rule is just constantly running. And whenever you happen to get a firing, so whenever, if let's say this is a nonlinear, Heaviside step function, so these neurons are Boolean neurons, let's say they're either zeros or ones, then if they both happen to be on at a particular time step, then we are going to increase the weight of the upstream neuron on the downstream neuron. And if they just happen to not be firing together at this same, so one of them's 0 and the other one's 1, then we may decrease that weight. Let's say instead of being zeros and ones, it might be 0, it might be 1 and -1. So, so let's say, for example, we'll say that the output is in -1 and 1. So here we see that if their outputs match, you get a reinforcement of the weight. If their outputs mismatch, you get a reduction of the weights. And so this is one way that we can implement this with a conventional artificial neural network. And so we can see then how this is useful for pattern learning. To kind of imagine how this whole thing works, then, and you can think of this in the case of a convolutional neural network, a computer vision application, for example. Let's say I've got pixels. So let's say I have a bunch of data sets that, and I'm just going to cut up into 5 by 5 grids. And so these 5 by 5 grids, I can imagine this is like, these just kind of prototypical inputs. And I've got a bunch of inputs that, let's say, look like this. They have a, let's say these are black and white pixels, and it kind of like all of the ones in this top group kind of look like a U. And then all the ones in this bottom group kind of look like an A. And so this is kind of, U type and A type. And these things get fed into an artificial neural network. You say with Hebbian learning. And then I get these outputs. And maybe these, the outputs of these things are neuron outputs that look like, they're just bit strings, for example. And so I get outputs that maybe I've got 8 bits. So I'll just put them in groups of 4. Or groups of 2, sorry. So I've got a bunch of these outputs that, after they come through the neural network, it just so happens that, what's gonna happen is if I run a bunch of inputs that look like these, then there will be neurons that just topologically, because let's say there's a bunch of fully connected networks, there will be neurons that just happen to fire together because they see this pattern over and over and over again. And so every time through this, we see there's a bunch of the data that cause the neuron attached to this pixel, and the neuron attached to this pixel, and the neuron attached to this pixel, this pixel, and this pixel. These 5 neurons will frequently fire together. And if they have connections to each other, then that means that their mutual influence on each other's input weight is going to go up. And likewise, downstream neurons that are connected to each one of these are also going to have their weights that they're going to fire together, and then their weights are going to go up, and so on and so forth. And so what will end up happening over time is, and there's a question, is this an alternative to backpropagation? If I knew, backpropagation would be good if I knew a particular output that I wanted to have coming out. I could say, for this output and this input, I want you to generate this output and figure out what weights go on in here. In this case, I want the neural network to create a lower dimensional encoding of patterns that I'm not sure are even there. But I feed it with data that has an over-representation of certain patterns. And I want the neural network to learn those patterns are there. So that's why it's kind of, it's referred to as associative learning. So if a baby's walking through the world, there might be some correlation between a door slamming and a vibration felt on the ground. Now, initially, the baby doesn't know that those two things go together. But over time, after it hears the door slamming and feels the thing moving on the ground, it forms an internal representation that ends up strengthening the weights from both of those together, so that inside its head, when it forms a representation of door slamming, either the rattling on the ground or the door slamming sound will end up both triggering the door slamming output on it in its head. So that's effectively what I'm doing, is I'm feeding these neural networks pixels, which initially the neural network does not know there's a correlation between the pixels. This is the sound of a door slamming. This is the feel of a door slamming. And it doesn't know that these two things are related to each other. But after it sees it over and over and over again, that when you get these 4 pixels, you also always get this one, it starts forming an internal representation. And that internal representation can be exported, hopefully in a lower dimensional space. So this is related to that auto-encoding out here, so that maybe this pattern that is formed inside the neural network shows up maybe as these 2 boxes. And then all of the examples that look like the A down here end up forming another output. You know, I've got maybe these 8 bits on the output, which happen to be these 3 boxes here. And so over time, what we learn is that we learn that this is the neural network's internal representation of what it means to be a U. And this here is the neural network's internal representation of what it means to see an A. And instead of, now it'd be one thing, like in autoencoders, we had a supervision that was fed back into here. But in this case, we're just allowing the neural network to find these patterns, to find these correlations, and then looking at its latent variables inside there and finding out that, aha, whenever I show it an A, this part of the neural network lights up. It must have formed the concept of an A, and that concept is encoded by these variables that I can extract on the output of the neural network, and vice versa. So initially, I give it a U, and I don't see any useful difference between these. But over time, I feed it U's and A's, and what I end up finding is that the things that I show it as U's get a consistent representation, and the things I show it as A's get a consistent representation. It might be that they share a neuron in that representation, but over time, if I show it more and more and more of these things, what's probably going to happen is the neurons that they share in this are going to drop out, and so that I end up getting a mutually exclusive set of a U and an A. Maybe or maybe not, but that often tends to be the case. And so that is a very alternative way of forming these kind of lower dimensional, well, they don't actually have to be lower dimensional, but that's an example of how Hebbian learning can be used to extract patterns in a set of data that where you may or may not know that those patterns are there, but the neural network learns them over time through this online learning. And then if you actually, it may be that you take this robot and it's learning these patterns just like the baby crawling around, and you put it into a new world. And in that new world, the patterns that used to be correlated aren't correlated anymore. Well, the Hebbian learning will notice that things that are wired together aren't firing together. And when that happens, it will then reduce those weights. And so gradually over time, it will form new representations of the new correlations it sees in that world. And so that's an example of how we can use this online learning to do pattern extraction and allow it to sort of do a lifelong learning. And this gets even more interesting when we go into spiking neural networks because of the hardware architectures that are available that can kind of do this on the fly without us even having to implement a computational update rule. And that's what I'll start with next time. So in the last minute or two here, are there any questions about this example, this kind of traditional neural network example with Hebbian learning in this kind of update rule? And here you can view the learning rate as sort of how much you trust your history in the environment. So how quickly are you willing to forget patterns that you've experienced and learn new patterns? All right. All right, so in that case, we will start Wednesday right on spiking neural networks and the hardware implementations that have started to be built from those. Some things that you might have heard of, like Intel's True North, for example, or I'm sorry, IBM's True North, and then we'll transition to future directions, which which relate more to the physiology of neurons and making them even more lifelike. I think I haven't released that. So basically at this point, you guys have submitted all of your project proposals. So your next deliverable, the Wednesday of the last official week of class, that's when you upload your presentations. And your uploaded presentations, you'll then do peer reviews from that Wednesday to that Saturday. And then I think I'm having you then upload your final reports on that Saturday as well. So you'll basically upload a presentation with whatever the 10 to 15 minutes, and I'll release these assignments on there on Canvas. I just hadn't done some copy editing, but that's the plan, is that Wednesday of the 15th week of the semester, so the week right before finals week, you turn in your 12 to 15 minute presentation. Then you're gonna do the peer reviews from that Wednesday to Saturday. So everybody reviews one other presentation, submits your peer reviews, and then you submit your final report that Saturday. And I use the peer reviews and the final reports to give you those grades. I would say I would start, especially if you feel like you have clarity, I would just start working on your final projects, and I will jump in if I see a major problem. But yes, if you've already kind of got an idea, the main function of the proposal was to just make sure that you were thinking so you'd have plenty of time to implement this. So you've already submitted that deliverable. I will, if I see something that I notice is like, seems to be really wrong, then I'll contact you. But otherwise, if you don't hear from me, I think you should just go for it. So don't wait for extra approval from me. Just work on implementing your demo, and feel free to vary from your proposal. The proposal is not meant to be a binding document. All right, any other questions? Okay, so in that case, I will, okay. And then I'll answer this question, and feel free to hang on if you'd like, but otherwise you can feel free to leave as it's 4:22 right now. So there's a question in the chat. In this example of Hebbian learning, what are the output of the internal representation of the input? So in the case of Hebbian learning, it's possible that the internal representation may be more complex, and the output is something that is in a more human readable form, or a more human processable format. So I'm kind of leaving out, there's a lot of application specific. So, but in general, it's just that imagine you have an application where you want you know, an 8-bit representation of patterns, which sort of suggests what you think about the sparsity of the pattern space that's out there. And then so the Hebbian learning will sort of hopefully provide you a useful clustering. So you can basically view this as a kind of clustering algorithm. Where this is, yeah, I could say maybe an online clustering algorithm, where these you can view as IDs of the cluster. Any other questions? All right. In that case, I'm going to stop the recording.